Hey, good morning or good evening, everyone. Welcome to this class. This class will help you understand the ASCE 716 requirements for soil properties and profiles used for site response analysis. Again, this slide shows three major components for the site response analysis. I talked about input motion in the previous class. And this class will focus on how to determine the soil profiles and properties. That include the shear modulus density, shear wave velocity, and the soil layer thickness. Let's look at the code requirement first for the soil profile and the property first. The requirements are in the section 21.1.2. So I highlight something I think they are important for the soil profile and properties in red. So first, your soil profile should base on the model should base on the low strain shear wave velocity, and that can be determined from the field measurement for the soil, for the similar soil in the site vicinity. And at the same time, you need to consider the uncertainties in the soil property. So what does that mean? I'll talk about that later. And the last situation is, for example, if you have a very deep soil site, you cannot drill a hole into the bedrock. So then you need the code allow you to terminate the soil stiffness at the site class D, defined in chapter 20. And then you need to develop the input motion based on the site class D spectrum. So in the previous class, I talked about the input motion should be developed at the bedrock. So if you cannot drill to the bedrock, so what you can do, basically, you can scale your spectrum up to the either site class D or site class C spectrum, then use that as target spectrum for input motion. Then you use that input motion for site response analysis. In the code requirement, there is a typo. The site coefficients should be in section 11.4.4, not 11.4.3. That's the old section in the ASCE 710. So what is the no strain shear wave velocity or shear modulus? So this slide will show you the shear modulus with the shear strain. So as you can see, when the shear strain is increased, the shear modulus reduce significantly with the increase of the shear strain. So, and this as showing as this blue dash curve. This slide also shows the different field test and how they measure the shear modulus at different shear strain. For example, the geophysics test, they measure the soil modulus at shear strain about 10-6 to maybe 3 or 4 10-6. And if you look at the right-hand side, the penetration test, mostly for the SPT or CPT test, they are measured the very large strain. Basically, they need to shear the soil, feel the soil to test the soil strains. So when we see the no strain shear modulus, we typically talk about the geophysics test. It's about the soil strains at the 10-6 or to up to the 3-4 10-6 shear strain. So, before you measure the no strain shear wave velocity VS, you also need to do the typical site geotechnical investigation and lab testing to determine the soil type. You still need to do the index property testing and also some basic properties like the unit weight. If you have a clay, you need to know what is the cohesion for the clay, either clay or sand. Then there are a couple ways to measure the VS. The first is the direct measurement. So that's the geophysics test, what I indicated in the previous slide. So basically that includes the seismic cross-hole or downhole test, SASW or RAMI test. And the code also allows you to use some correlation to calculate either the nose strain shear wave velocity VS or the Gmax, the maximum shear modulus. There are a bunch of correlations. I will talk about that later. So this equation is very important. So the nose strain shear modulus Gmax, basically the shear modulus at the shear strain level 10⁻⁶ is equal to the soil density times the nose strain shear velocity VS square. So this is a very important equation for calculate the shear modulus from the shear wave velocity. So this slide just demonstrate the seismic cross-hole and downhole test. For the cross-hole test, you need to drill at least 2 holes. So then you put your source, seismic source, in one hole, and make sure your receiver is at the same level. So you put your receiver in another hole, then you trigger your resource. The wave will propagate from the source to the receiver through the distance delta x between the holes. So the delta x typical we know either is 5 feet or 10 feet based on the ASCE 7. It's ASTM, the seismic cross-hole test requirement. So this is the most accurate way to measure the soil shear wave velocity. The shear wave velocity is equal to the delta x divided by the delta t, the time of the wave travel from this hole to another hole. But the issue for this is very expensive for this test. Based on the ASTM requirement, you need to drill not 2 holes, 3 holes for this test. Basically you drill a third hole here, then you just use as a backup to double check the shear wave velocity calculation is correct. So it's very costly because drilling hole costs a lot of money. So then this side, right hand side, is downhole testing. So what they do, they have the resource. They have the source at the ground surface, and they have the receiver in the hole. So they only need to drill 1 hole, and the wave propagates through this way. So they base on the time for the at different depths for the wave traveling, they can calculate the shear wave velocity of this layer. So basically this layer is from Z1 to Z2. As you can see, the seismic wave just propagates through multiple layers. So this method sometimes is kind of estimate of many layers for the shear wave velocity. So it's not as accurate as cross-hole testing, but you only need to drill 1 hole. You reduce your cost quite a bit, and At the same time, you can do this test for the CPT test, the concentration test. So they call that as seismic CPT test. Basically, you just put your geophone receiver at the tip of the cone. When you push the CPT test, you can run this downhole test to get the shear wave velocity. So for that way, you don't need to drill a hole. So it reduces the cost significantly. SASW, spectral analysis of surface wave. So this method just gained popularity recently. It based on this figure because the ASCE wave, the rainy waves, is a surface wave. The rainy wave velocity, as you can see, is very similar to the ASCE wave. So what they do, they just have a source at ground surface, then they have a kind of array of the receiver at the equal distance. Either they have a 12 receiver or a 24, even more, or they have even multiple lines of the receiver. That one is called MASW, so multiple channel analysis of surface waves. The surface waves has one properties. They are dispersive, so which means when the wavelengths go longer, this wave will go deeper, but the wavelength is shorter, the wave is typically near the ground surface. So basically, based on the frequency, it can separate the wave at different soil layer. So if you, for example, if you based on the data, just measure this surface wave back to the receiver, so you can calculate the rainy wave velocity for this layer. So if you go deeper, the wavelengths became longer, so you measure the different wave. So once you have the rainy wave velocity, you can use some correlation to calculate the shear wave velocity, Vs. This is give you kind of summary, the most commonly used correlation to calculate the shear wave velocity. All know is the maximum shear modulus based on the SPT or CPT data. So the first one is for sand. So there's some typical value for the K2 max. You can check the Kramer's book, Geotechnical Earthquake Engineering, to know what K2 max for the different type of sand. The second one is also for the sandy material. It's based on N60. The sigma V prime, the effective vertical stress, I believe the unit is in the PSF, is a pound square feet. This equation 3 is for the cohesive material. So SU is under shear strength. Last one is you calculate the maximum shear modulus based on the CPT tip resistance. So once you have the Gmax, as the equation between the Gmax and the Vs, you can easily calculate the Vs. So in the code, it requires you need to consider the uncertainty of the soil properties. The reason for that, because typically for one project site, even you have some kind of variation of the soil profile and property, you typically to run one site response analysis to cover the entire site. So for that reason, you need to consider the variation of the soil profile in your project. So to do that, you have to consider the uncertainty of the soil property. So the uncertainty of soil property, there has two folds. One is, as shown in this figure, just the variation of the VS. Another issue is just they could have the different depths of the soil profile to the rock. So to do that, first you need to determine the best estimate soil profile from investigation, lab testing, or correlations. So that best estimate soil profile is typically the average soil profile for the project site. Even for shear wave velocity, that's typically the average value for that soil layer. So after that, you need to determine the lower bound and upper bound soil profile. So there are two approaches for the upper bound or lower bound soil profile. One way is to bounding all the investigation lab test results. So if you run a lot of shear wave velocity testing, so your lower bound could be all the value at for each layer at lower bound. The upper bound certainly is in the upper bound. Another way is just that you base on the best estimate soil profile, then you vary the stiffness by 50%. So this is in the commentary in ASCE 716 code, which I recommend you use this approach because it's in the commentary of ASCE 716. So that's 50% for the stiffness. We know the stiffness is proportional to the square of VS. So the variation of the VS would be 22%. So basically you use this shear wave velocity, you reduce 22%, you got your lower bound, and you increase 22%, you get your upper bound soil profile. So all these three soil profile will be used for the site response analysis. So in the code, you said there could be a situation you cannot drill a hole to reach the rock. So the code then said, it allow you to terminate the soil profile at the values used to define the site class D. So basically, at the location, the VS greater than 600 feet per second. However, I won't recommend you terminate your soil profile at site class D. The reason for that is, based on the code, you have to adjust your base motion spectrum, basically the target spectrum, upward. So basically you scale up, use the site coefficient in section 11.4.4. But as what we presented in previous class, right now ASCE 716 has dramatic change. If you look at the table for FV for site class D, you cannot use those coefficients to get your target spectrum. So for me it's kind of loophole. So if you read this requirement, you need to do the ground site specific ground motion analysis, and that's what we do right now, try to do right now. So if I want to do this, I would recommend you terminate your soil profile at site class C, where the VS greater than 1200 feet per second. So if you do that, you can see here is straightforward. There's no any additional requirement for the FV coefficient, so you can use those coefficients to scale up your bedrock spectrum to site class C spectrum and use that as target spectrum to select input motion for site-specific response analysis. So this class, I give you a general description about how to determine soil profile and properties for the site response analysis. So basically, we determine the approaches to calculate shear modulus, density, shear wave velocity, and the synchronous. And in the next class, that will be the final class of this series. We'll talk about the soil model used for site response analysis and how to deal with the results of the site response analysis to meet the additional code requirement. Well, thank you all for this class. Please let me know if you have any comments and suggestions.